So, from your experience, what makes CFD hard for people to learn?
You don't say to yourself, I can play now or I can speak now that language. It's just a question of degrees. So I think you're conscious that you're just developing a kind of competency over time. And so the definition of competency is the confidence to perform, in our case, CFD analyses repeatedly to some standard in a timely way. And I think when I talk about musical instruments, speaking a language, that kind of fits because firstly, the good time bit, sure, you could play the note, but can you kind of keep churning this thing out? Same with language, can you just have different conversations with different people? It has the confidence to do this. And I think with instruments and language, you can see it. It's like, are you confident enough to have a conversation with a native speaker? Are you confident enough to perform, in front of people? And so I like that, and I like to keep that thing in mind. So at the end of all that, I just think, well, CFD is hard. Why do we expect it isn't?
Today, I get to interview Chris Greenshields of CFD Direct, the architects of OpenFOAM. A special thanks to CFD Direct for sponsoring this episode. Chris is the managing director of CFD Direct and has given over 850 days of CFD training to students worldwide. He has over 25 years of OpenFOAM experience and is the co-author of Notes on CFD General Principles. I hope you enjoy our conversation, and please like, subscribe, and hit the bell so you don't miss an episode. Welcome to the podcast, Chris. It's really good to have you on the show, and I'm really excited to talk with you today.
Nice to be here. Thanks for inviting me. Thanks a lot.
Yeah. So one of the things I'm always interested is how people got introduced to CFD. Could we start there and you share your experience of what was your first exposure to CFD?
Mine's a bit unusual. I don't think you'll have heard something similar to this before. I got involved in 1996, but I was at Imperial College. I'd completed a PhD in fracture mechanics, and I moved on to another project, and I basically met Henry Weller, who had started writing foam in sort of late 80s, I think 89 or so. And he got that to a stage where it was solving CFD by about 93. So it's a few years, maybe 3 years after that. And in my first meeting with him, he kind of showed me foam, and foam's, I guess he pioneered the idea of scientific software in modern computer languages, modern programming languages like C++. And the reason for doing that was just to manage the complexity that the software was going to get complicated. It's a big piece of software. And in our first meeting, he showed me the solver, which was IcoFoam, simple basic CFD solver, incompressible flow, and so on. And in that, you'd have the top level code with kind of algorithm structure, and then it had these lines of code that looked like equations. They were equations with functions that represented each term in the equation. And it kind of amazed me. I mean, I couldn't imagine software even looking like that. I had seen, say, for some Fortran codes, I've been exposed to those, and they look nothing like it. And what I thought at the time was that working with Fortran codes was really like an exercise in concentration. You just had to kind of work through lines of code and make sure your I's and your J's and the K's were kind of the right way around, and that looked like pain to me, really. Whereas when looking at OpenFOAM, immediately I thought this could be a much more creative endeavor where you've got much more power at your fingertips to do different things. And probably the best example of that, or an example of that, came actually some years later. That we were working on a slowly moving flow, so you could probably call it creeping flow, low Reynolds number. And the code was blowing up. And at the time, there was a kind of mantra that if you were doing creeping flows, you had to have a fully coupled solver. And Henry was there. I think Matthias Janssens was there, and we were kind of talking about it. Henry saying, why doesn't this work? And then he just said, what would happen if we didn't solve the momentum predictor, the sort of first stage? So this is in a kind of classic piezo-like pressure velocity coupling approach. He said, why don't we just not solve momentum predictor? But because of the way the code was written, that just meant commenting out one line, recompiling the application, which took about 20 seconds, then pressing go on the code took a few more seconds. And within half a minute, we kind of worked out that this mantra was wrong because the code ran fine, and it just meant, yeah, in order to do low Reynolds number flows, you just don't solve the momentum predictor. And that for me expressed the kind of power that we had with OpenFOAM that didn't exist with say a Fortran code.
Yeah, that's very fascinating. I'm always interested to hear how people get into it, because one of the things that I get a lot of questions about is people assuming they have to have this formal training. And although that's good, right? That's good. But I just love how you shared this was after your PhD when you got into it, right? That was your
Yeah, bear in
exposure.
mind, my PhD had nothing to do with CFD. So I did a PhD in fracture mechanics. And so this was kind of a completely new direction for me. But I just happened to be in a certain place at a certain time. But I think the difference was that to me, the possibilities of OpenFOAM compared to, say, conventional Fortran codes was immediately obvious. It kind of blew my mind.
Yeah.
What I also discovered that day was that there were other people who just didn't see it at all. So I remember taking the code, I printed it out, took IcoFoam back to my desk. We're in an open plan office. I showed the guy in the next booth to me, and it had no effect on him whatsoever. He just wasn't, and he was kind of doing CFD. So, so that was two things I learned in the same day. It was quite a surprise to me that someone else just didn't see it, what I kind of saw.
That's really striking. What do you think? Because I've experienced that as well, even recently. What do you think allowed you to see it? Was there something in the problems you were solving where when you saw it, it was like connecting some dots that hadn't been able to connect before? Was there something else or another element that you think contributed to you being able to see something more?
I think it's a kind of, well, it's a sort of appreciation for sort of generalization that instead of
Mm,
looking at everything in terms of, or seeing bits of code and saying everything is going to be written from scratch with, particular purpose. So, that's the way it's going to be. With what I saw in OpenFOAM was uh, this sort of general framework that just seemed so powerful. I mean, I could, to me, it looked like, well, I could write another equation now and I could put in whatever terms I like, but it's still going to be like 4 or 5 lines of code. So it's purely like sort of an economy somehow was the thing that impacted me. Is that, yeah, the economy of writing code like that got to me. I would also
yeah.
say possibly, it might sound a bit fanciful, but there's it was an elegance to it, and almost like a
Hmm.
beauty to this that kind of captured my imagination. But yeah, it was a shock. It was almost like a shock to see something like that
Yeah.
at that time.
Yeah. That's really neat. Thanks for expounding. So, jumping ahead a little bit, you've been all over the world teaching OpenFOAM. You have 700 days of plus days of training. I don't even know what that number's up to now. That was the most, okay, 850 um, of teaching CFD and OpenFOAM. So, from your experience, what makes CFD hard for people to learn? And one of the things I've seen is it's this confluence of, to even speak the language and understand what people are talking about, you have to have at least some level of depth in multiple fields, right? Talk numerical algorithms, computer science, the physics of fluid dynamics. But could you speak to that? What are things that you've observed in your vast experience of teaching and training about CFD?
Well, before we talk about maybe what's hard about it, I think we want to
Hmm.
just sort of set some level of expectation, because when I think about this, I'm thinking about people who are often starting CFD with no prior experience. So you're developing a new skill from scratch. And,
Hmm.
um, and if I then say, well, imagine if I was doing that, what happens if I wanted to like learn a musical instrument? I don't know any musical instruments. Or if I want to learn a language, I have a confession. I am learning a language, very slowly. Um, but what I want to think about is how hard is TFD compared to those things. And I think the thing with the examples I've given is that you don't you don't ask yourself, you don't say to yourself, I can play now or I can speak now that language. It's just a question of degrees. So I think you're
Mm.
conscious that you're just developing a kind of competency over time. If I was learning the two things I've just described, I'd be giving myself a pretty long time to do it. So I think there's kind of an over expectation. I think that often comes from managers and supervisors who are instructing whoever it is that they need to do some CFD. And what I have experienced when I've been doing training, seeing people who are evidently under pressure from those managers and supervisors. Um, Now, I think we need to reframe it in terms of competency, right? So achieving, it's a skill, you want to achieve a level of competency. And there was a guy that I heard a talk by a guy called Robin Hoyle, who said we need to define competency. He's a kind of general training expert. I sort of twisted his definition slightly, but I still love his definition. And what it comes down to is, so the definition of competency is the confidence to perform, in our case, CFD analyses repeatedly to some standard in good time, like in a timely way. And I think when I talk about musical instrument and language, then or learning, speaking a language, that kind of fits, because firstly, the good time bit, sure, you could play the notes, but you might play them very slowly, right? Secondly, the repeatedly bit is that, yeah, you could, rehearse one song, but can you kind of keep churning this thing out? Same with language. Can you just have different conversations with different people? But the big word in that, in his definition that I think makes a difference is he deliberately prefaced it all with confidence. He says it's the confidence to do this. And I think with instruments and language, you can see it. It's like, are you confident enough to have a conversation with a native speaker? Are you confident enough to perform, in front of people? And so I like that, and I like to keep that thing in mind. So for me, right, I think coming back to the question, why is it hard? I think the question I'd like to sort of talk about is, why do managers have somehow misguided expectations that it's going to be easier than they think? And I think one reason is that they all use software in some way, and they think, I know how to use this bit of software. I'm going to apply that to CFD. It's just a question of using some software. Now, even if you're talking about, say, Word, right? Just knowing how to use Word doesn't make you a competent writer. If you go more complex, like accounting, let's think of a scenario. Someone could teach you, say, how to add a journal entry to defer revenue, right? But if you make a mistake, then your books are never going to balance if you don't know what deferring revenue means. And that's where the technical knowledge of the subject of accounting comes in, right? I think that's one of the bits people miss with CFD, because CFD is going to be I think we have to stay more complex than accounting, or running CFD software is more complex than accounting software. The reason is because accounting software really involves one subject, which is bookkeeping or accounting, depending on how complex you tend. Whereas CFDs look really 5 things. I mean, you've got fluid dynamics, which I would argue is more complex in itself than accounting, partly because accounting creates a set of kind of parameters in which you work, whereas fluid dynamics much more open-ended. But then on top of fluid dynamics, you've got the other 4 elements, I think, which are geometry and meshing, numerical methods, data processing, which is really about extracting the information you want to know about from your simulation. And then you've got just the subject of computers and programming. And in amongst that, you could be talking about launching parallel runs. So clearly with accounting software, you don't do parallel runs, you don't have OpenMPI running and all that kind of stuff. And on the programming side, particularly with OpenFOAM, you might want to write some software to give you a better outcome, particularly around extracting data or initializing cases or that kind of. So at the end of all that, I just think, well, CFD is hard. Why do we expect it isn't? That's how I would put it.
That was so articulate, Chris. That's fantastic. Yeah, I love the degrees of complexity. And I know that that's very encouraging to our listeners, because when you, who was it? Maybe I'm going to forget the quote, but half of solving a problem is clearly defining the problem. And I feel like now with that clear definition, things become, your expectations are closer aligned to reality of it's going to take time. And not every job, this is another thing I've observed, not every job requires the same level of competence to perform well in CFD. And there's no alpha judge out there that says you are now certified as a CFD expert, right? For what? Under what circumstances? For who? So thank you for delving into that nuance of how we should think about that. That's excellent. And I noticed some beginnings of, I think that's how you start your book here, of complexity, the definition in there.
Yeah, that's right.
Or competency, sorry, the definition of competency.
That's true. You're right that I kind of credit Robin Hoyle in the book with that quote.
Yeah.
Or that definition of it. And it's something that I must have heard it 10 years ago. I saw this guy do a presentation and it stuck with me, and it kind of guided me in writing training material and producing courses, which is all about improving competency. So it really focused my mind on what I was trying to achieve with training, a good 10 years ago, which I'll probably expand on a little bit later here.
Yeah, sure. I wanted to jump to, which is probably a natural segue, of what are the most common mistakes, right? One mistake I think that we've just outlined is real expectations and what's realistic. But what are some other mistakes that you specifically see newcomers make to OpenFOAM?
Yeah, the first thing is that newcomers often simply don't know where to begin. So I kind of call that keyboard freeze. They just sit there. They don't know what to press, which I think feeds exactly into that Hoyle definition of competency under the confidence word, right? They just aren't confident enough to click the first key or press the mouse for the first time. I think one of the reasons, in fact, that some of them are like that is because they're so worried about making a mistake. So when you're saying what are the common mistakes that they do, well, some of them may make none because they don't actually do anything because they're so worried about making those mistakes.
The fear of making mistakes is the biggest mistake.
And in some way, I think that's connected to another big problem I see with newcomers, right? Where and this often comes down from their management. The management tasks them with a problem that they want to solve. The newcomer takes it and in their mind that they know what this problem is that they want to stimulate. And it could be a case with a number of complex issues. As you said, right, that there is a range of complexity here. But imagine if it's one of the ones that at the higher end, let's say, at least beyond the middle range, right? The big mistake they make is they seem to think that what they need to do is go from nothing to a fully complete simulation with all the complexity in it in one shot. And that if they do it right, everything will just work. Basically, that there will be no mistake. Now, the reality is that nobody can do that. So when we even talk about the question, what are the common mistakes? What we have to recognize is that mistakes are part of the job. Like we would all make mistakes. The question is what we do about it, right? And how we manage that. But I think both of these things, right? The keyboard freeze issue, the one-shot solution approach, they're caused by a fundamental failure to understand that CFD needs to be approached like a classic design problem, which follows a kind of iterative loop where you go design, build, test, evaluate. In the first loop, you create the prototype, and then you follow on with more loops, starting with small changes, and you iterate, right? So, what we're talking about in the CFD setup is design is the consideration phase where you work out what you want to know from your CFD. You work out what you want initial prototype simulation to look like, keep it simple, in particular, keep it quick to run. So run with use a very small mesh. I guess small mesh is part of keeping it simple, is reducing the complexity of things a little bit. But once you've got that clearly defined, the build phase is where you configure the case within the software. The test phase is where you run it. And while you're running it, you want to make observations. You want to, extract bits of data to help you understand what's going on. And that's for the evaluation phase. Take those observations, make assessments, consider what you want to do next within the next design step, and then you're looping. And as I've said, we're going to make mistakes. There's stuff going on in CFD. There's bound to be mistakes made. And by the way, even the word mistake, it can be a fine line. It doesn't necessarily, a mistake is not necessarily an error. It's just it's something that didn't work out right. The key is that the better CFD engineers, and in fact, I would say, you could almost say, well, the better cello players, the better linguists or whatever, when they're practicing, what they do is they make smaller changes within the design stage, but then they iterate quickly around the loop and evaluate quickly and effectively. And that's the trick. If you make small changes, in fact, if you make changes that are so small, it's only one thing, then if the case fails, you know exactly immediately what caused it, because it can only be that one thing. So that's the real trick: is small incremental changes, iterate like crazy, evaluate effectively. And you said earlier, I think, that a big chunk of the problem of doing CFD is kind of outside of the software. Well, if I say design, build, test, evaluate, design and evaluate is outside of the software. So kind of half of it is outside of the software. And so even when we talk about training, like training CFD, we need to cover things that aren't really about the software at all. They're about, those two other aspects that within that loop, within that iterative design loop.
Yeah. Yeah, that's excellent. Yeah, excellent, excellent explainings. So do you find that these are common across the globe? Like, you've been all over the world, right, of teaching and training, and do you find that maybe there are some variations, or is it pretty consistent core of what people really need help with in your experience?
If you're talking about, um, if you're talking about sort of say the part about training over the world, and because in the early days, particularly, I did actually travel to places. So, but also we do a lot of training online. People attend from different parts of the world.
Mhm.
Probably the thing that one thing that's a noticeable difference, I think, it is actually the pressure the CFD engineers are under from management in different parts of the world. So I think in certain cases, there's uh, pla people or places that are desperate to just solve the next problem. So they just want the next problem solved. Um, that's the horizon of their kind of thinking. Um, in terms of say, you know, knowledge, fluid dynamics, etc. There's certainly variation there as well. In terms of being comfortable with computing, there's variation across the world as well. One thing um, that has changed a little bit, I mean, a lot, actually quite a lot from at least from my experience, is what people need more today than when I started. Because um, the I started training a long time ago. It's like 2008, and this is all around OpenFOAM. OpenFOAM, you could probably say, wasn't really fully mature software there. At that time, then in 2008. So initially, what you were just trying to do was to take participants through the general mechanics of running the software, and and often in some cases, you were even teaching them how to deal with or kind of find workarounds to certain limitations. It was that kind of thing that was going on. But OpenFOAM moved forward, you know, pretty quickly. And I'd say it was pretty mature maybe 10 years ago. We started CFD Direct in 2015. Some of us, Henry Weller and so on, started the company. Fresh start really. And at that point, I wrote entirely new courses, and then the emphasis had changed because I wanted to get the kind of processes and procedures, if you might want to call it workflows, to help people set up CFD problems from scratch. And in fact, at the time, what we did is to put loads of kind of new things in the code. I did some. Henry did some. Henry worked on kind of packaging function objects, which are the tools that help extract useful data. So we were focusing there on the sort of observational part, in the kind of test part of the design cycle, getting stuff out that we could evaluate. I did a lot on. I created these things called template cases, and they were a sort of a case that was designed to help people go from scratch to a prototype case really quickly. There is that design loop, but you've got to get going at some point. And what you want to do is hit the prototype as quickly as possible and have it working. Once you get that working, then you're in the loop. You're in the design loop, and you're away. Right. So template cases, we had kind of sets of standard configuration files, tools that allow you to copy them into the case quickly, put in things like tab completion, which is just purely a practical thing to make the code easier to use. So a lot of work went on, driven by the training, to make OpenFOAM easier to use. And it was all about prototype cases and all that kind of stuff. That's worked quite well. So, and we carried on making the code easier to use to the present day. So, adding more tools along the way, things like foam info to get information about models, foam talk to get similar sort of stuff. foam find now to search for code. The outcome is you can sort of see that people were having fewer problems using and running OpenFOAM, that they were okay with that. So from the design cycle point of view, the build and test phases were much better covered. That was fine. Getting prototype cases up and running from scratch, factoring data, that was all okay. But as soon as you feel that that's going better, in fact, when you're running training, what you notice is that the bottleneck, that they kind of leap out at you. And that's one advantage of doing in-person training, is you're observing how the participants behave and respond. So it's very obvious then that the areas that the participants were struggling with are effectively the design and planning phase and the evaluation phase at the end. And as we said, they don't really involve the software itself, but it's where knowledge, expertise, and kind of acumen come in, right? The problem I kind of hear about all the time, particularly then when before COVID, when I was doing this in person, and people were, we had a bit of free time to have discussions and so on, is that people were saying that their managers or their, let's say, the academic supervisors, if they're doing a PhD, weren't able to contribute much, in some cases nothing, to their knowledge and experience. And I remember in 2019, one class, a student sort of made the point that they received no support at all from their supervisor. And all the other PhD students who were in that class just nodded in agreement. And the original person basically had sort of tears in their eyes, but it was clearly out of relief that they were not the only one who was being shortchanged on supervision, basically. And I remember that's 2019 because that was one of a few things that kind of were the final straw for me, where I ended up saying, we need to write a book. So I thought I need to do something here. They aren't getting the information that they need. Let's just deal with the knowledge aspect. And so literally after coming back from the States, I think at the end of October, about a week later, I started writing the book. So I basically went to Henry and said, here's what I've just seen. We need to write a book. He said, okay, off we go. So November 2019, started writing the book. And it came out in April 2022. And it's free on doc.cfd.direct. And then we also self-published it. So yeah, you've got a copy there. So we self-published it through Amazon, which was turned out to be a good experience. One of the things about that was that we just didn't have it being sold at a price that we thought would, be restrictive. So it sells for kind of, I think in the US it's like $30 or $29, something like that. And self-publishing, it's fun. I mean, you have to do everything. So the front cover, you have to create and everything, all that stuff. So yeah, it was kind of good. And the point of the book is providing knowledge. So it's just recording some knowledge that we labeled as sort of general principle. But in the last couple of years, I've kind of realized that knowledge needs to be applied. It's not immediately obvious what you necessarily do with that knowledge. So what we've done recently is creating a new course called Principles of CFD. That's taking the knowledge, helping people with the design and evaluation stages principally. And we're running courses actually now in person again. So that course we're going to do in person. Got venues booked in Cologne for September and then in Chicago in October. And I really am confident that people who attend that course like get a big boost to their CFD competency. Part of the reason is because in putting it together, I'm surprised myself about certain connections between the knowledge and what you can do with that knowledge, how you can help it in there, how you can use it in those two stages, the design and the evaluation stage.
Yeah. That's really, really insightful to see the evolution of learning over time, right? We talk about gradations of learning CFD, but even just as you're talking, that process never stops, right? One thing I just want to point out is that the horizon always moves. Once you develop a certain level of competency, as you approach it, you continually move your horizon because you want to continue to improve and get better. And I think that's another element that a lot of people forget, of looking back to see how much ground they have covered, especially as learners, right? And what people have done. So
And
that's
as soon as you just use the kind of musical instrument example or language example, it's kind of obvious. You just don't say, I can play or I can't play. It's just degrees of ability, or degrees of
mhm.
competency. Again, that's the right
Yeah,
word.
yeah, yeah,
And and
yeah,
and so, but it's just being acknowledging that's the kind of process we're talking about. It's about building that competency over time, and not thinking that everything's going to, you're going to be an expert in 5 days or whatever, right? Yeah. So as soon as you think about those examples, I think you're thinking along the right track.
yeah, yeah. Just a note on this, I've made this post on LinkedIn before. I paid full price for this book, and I wish I would have bought it sooner. So you can get it online. I'll put a link in the show notes. But really, I have loved this book. It's a 2-page format, and I want to spend a little bit of time on that, right? So every chapter is 1 page, 2 page, or every topic. And you titled it Notes on CFD, right? The point, as you shared with me, was to distill kind of big picture essence. It's not a reference textbook. That's not why it was written. But I find myself, it's excellent to, I forget something about a boundary condition or a certain aspect, to flip through and see, okay, here it is. And then I can go look for another reference. But can you speak to the format of the book and why you did it the way you did?
Yeah, there's two things. The first, the first thing that inspired that format really came from training, and about 10 years ago, when I was creating the set of courses that we started at CFD Direct in 2015, I had a kind of blank sheet of paper, and at that point, one thing I thought about was that we may want to do the training online. And it felt to me that if we were doing it online, timing was a much more important issue, that you wanted it to be more modular, and know that for each module, it was a fixed duration. So you could fit everything in to a more rigid timing structure that you have on online training. And, um, and a good friend of mine, I had discussions that the idea for that came up with a friend of mine, a guy called Richard Jones, who's in who's he was an Australian, and I sort of worked with him for a period, and we talked about this idea. And at the time, we actually thought that a module, then, if we were going to have it fixed duration, we'd have a fixed number of slides, and effectively that we'd create a template, and we would we'd write every module to that template. And um, it 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 was now that we had an idea of 5 slides in 45 minutes. In practice, it turned out I needed more. So when I did it, I needed a few more than that. But there's a sort of I still go back to that day.
More minutes or more
Say again?
slides?
Yeah,
More
more
minutes or
slides.
more slides? Okay,
More
more minutes
slides,
or more
more
slides?
slides.
Okay, more slides.
So
Yeah.
I do go back to that day and just think about this somehow the kind of 5 slides principle that never quite was, but the idea was there, right? So that
Yeah.
one thing that influenced the 2-page idea. In, then in terms of calling it notes in CFD, the idea behind that really came from the fact that whenever I've had or others that have around me have had discussions with Henry about CFD, he very often would just write stuff down on a single page of paper. So he, if you said, okay, explain to me Piso algorithm, he'd just get out a blank sheet of paper and he'd write certain things down and a few arrows, and then you have it. There's your notes, right, on Piso algorithm, for example. So I wanted to get, so in my mind, I wanted, in a sense, well, to be able to transfer the knowledge out of his brain onto paper. And the way we worked was that I did the kind of writing, but on probably at least half the topics, I would just have a discussion with him. So I was kind of extracting from him his thoughts on certain things. It was a revealing experience because sometimes there were things that I'd never asked him about. And I think there's a good example. It's in the turbulence chapter. There's one, I think it's early on, the one about imagining kind of why turbulence is generated at a wall. And Henry had this, as soon as I talked to him about it, he said, I imagine some sticky substance on a surface and like a putty or a kind of glue that isn't quite gone off, and rolling my hand across it and it just rolls over. So it's that diagram. That's the one. No, it's not that diagram. I think it's maybe number 2 or something.
Okay.
It's like a sliding. It's a plate with rolling things on it.
Oh.
And so he described that, and so I kind of put it into words and pictures, but I'd never had that discussion with him before. That's the one. There's the diagram, right? And a lot of people have said, "Oh, I really like that diagram. I really like that idea," and I think it's indicative of maybe what they don't expect from Henry, which is he's got a very, is a mind that thinks in pictures, so really like that. And so it was a lot of fun because we had all these conversations, and there's, I don't know how many topics in the book, but you can imagine there was a lot of conversations about stuff, despite the fact I've worked with a guy for, decade. There were certain things that I I'd never talked to him about. And I enjoyed that aspect about it a lot. I also think, what I also came away with was that even when I thought I knew how remarkable OpenFOAM was, through writing the book, I kind of discovered new things that I didn't really appreciate, which in the end makes me realize that nobody really appreciates it, because I know that, 3 or 4 years ago, I didn't appreciate it the way I do now. And at some point I'll discover something in the future that will make me appreciate it again a bit more. But and that was all around the bit that the bit that related to that was to do with matrix construction and boundary conditions. And it was really about how boundary conditions are separated in OpenFOAM. So to get that modularity where you can just write a boundary condition in it as a piece of code, completely detached from everything else, the imagination to make that possible is kind of remarkable. And I didn't quite realize how smart it was until I was writing the book. So in the chapter on boundary conditions, it kind of dawned on me, and I was, I was taken aback, as I said, despite the fact I've worked with a guy for several decades.
Yeah, it's really neat. Yeah, excellent book. I'd highly
And
recommend it.
then yes, so the kind of couple of influences. Suddenly, I had this idea
Mhm.
about 2 pages, and in a way, I think the final motivation was that I get frustrated when I read textbooks, and you start this little section, and you you're reading, but you don't know when it's going to end. You don't know where it's going, and what you don't really know why you're reading it. But I think that's the
Mm,
problem, right? It's just meandering towards a
mhm,
result, and the result is perhaps the big thing, but the last thing in the hooks, in that section. So as well as so I thought, okay, if I could possibly write 2 pages, write each topic to be 2 pages, when people open the book, then they have that expectation that topic will not go on to the next page. So once they finish those 2 pages, it's done. And so it was really, yeah, a motivation because of frustration when I read books myself. Um, it was a little, what I'd say then is it was a little bit tricky to write that. I mean, you can imagine it's not easy. So I had to kind of pad certain things like images and stuff, but to get it right. But I think what it did help with
mhm,
is it enforced a kind of discipline that when you were writing about one subject, that's all you were writing about. If I found that I went to sort of 3 pages, it meant that really the thing that I was talking about was 2 subjects. I needed to break it up and create 2 pages.
mm,
Um, the other the other thing, coming back to that idea that you read a topic in some textbooks and the last equation is actually the thing you're looking for. I decided in a lot of the topics to reverse that. So what you'll see in subjects like, conservation of mass is I just come out and say what the equation is straight out. So there's a kind of reverse narrative where you just say, this is the result, and then go, oh, here's how we got there. I don't like the thing where it's, you know, the whole text is leading to the result. And only at the end you find out what it is you're aiming for. It's nice to know in advance what you're aiming toward. So that's another device that I used in the writing. I don't know, just somehow seemed natural.
yeah, yeah. Well, it's amazing. I've read a lot on pedagogical teaching and psychology, and that's one of the things people are finding is that when they can tie it to something to hang it on, then they stay connected. And it's amazing to see. Yeah, that was one of the things that stood out to me very clearly when I got this text was this is beautiful. This is here's what I need to know. Here's the supporting information. And now I know, yeah, it
It's
was very well
avoiding that
done.
voice in the back of your head when you're reading. It's saying, why am I reading this? Why am I reading this? And it just keep, and you get further and you still go, where's this going? I don't know. I mean, I'm interested. You have to tell me more about what you've read about teaching, because
Yeah.
um,
Yeah.
because I'm kind of interested. Well, I'm kind of pleased that I came to the same conclusion without actually knowing about the kind of things you've read about there.
Yeah, and I think it plays into a little bit in this conversation. So there's a book out there, it's called Start with Why, and it's definitely more business minded, but eh, I find that it has played a role in my learning of CFD. When I know why I'm learning difficult math, I can push
Yes.
through it
Yeah.
because I know why. I know this is essential for me to reach a certain level of competency that I want to reach. If I don't know why I'm learning that algorithm or this technique or this certain feature or theory, then it's very difficult to push through. And so knowing what the objective is up front, knowing why I'm doing this provides clarity and a reason for the effort that it's going to people don't mind doing hard things. They don't like doing hard things
Yes.
without purpose. And so when you can align purpose with hard things, that's when we thrive. That's when the endorphins are released, where all the brain chemistry happens. And that's when people really take off, is doing hard things with purpose. That's
Yeah, for
rewarding.
sure.
So, yeah. And I think that book was, yeah, it was easy to read. It was, yeah, anyway, you did a really, really good job with it. So, yeah. Yeah. So, one of the things I saw recently is Aiden Wimshurst is joining you for this teaching. And I went to see it and I saw that he joined CFD Direct. And I wanted to talk about this. You had a post on this, I think, on the website of feeling a need, and you've touched on it a little bit. The principles and applications of CFD, I think, was the course that's kind of new. But are there other changes that you feel like need to happen for companies to have enough well-trained, and again, well-trained is subjective, but to meet the needs of industry in training engineers in CFD? Because we're not using less simulation. No company out there is planning on using less simulation that I know of. They're using more, but what changes do you think need to happen to continue to meet that need?
Well, first of all, I agree that
That's fine.
yeah, you're right. I mean, there are more companies wanting to do simulation, right? So that places demand. I mean, where you just ask the question, where are the people going to come from to do that? I think if there's nothing, if there isn't a mechanism to feed into that system, then it becomes more challenging because there's a basically the supply just isn't there to meet the demand, and then people start moving companies. It gets the usual supply demand problem. So I think there's already a problem there.
Mm-hmm.
Um, now, well,
Mm-hmm.
I think if we go back, the companies have to have realistic expectations. We've kind of agreed that it takes time to train people up. I think then there's a question of tension of those staff, particularly in a climate where supply doesn't meet demand. So what do they do about that? And you talked about, you said it's about
Yeah.
well-trained engineers. Well, do they expect the people that they have to teach themselves? Are they getting, you know, informal
Source of
training
that.
from people? But I've already touched on that a
Where's
lot
that
of
training
people
coming from? The source of
complain
that.
they don't
Yeah.
get good support, right?
Mhm.
Um,
Right.
how do they know if the people that they've
Mhm.
got are well trained? One of the problems there is, we talked about the competency thing and competency, at least Robin Hoyle's definition, he talked about defined standards. If you're doing a musical instrument, you can take exams to prove that you're a certain level, but in CFD, we're lacking defined standards. I suppose then, in the absence of those standards, you might have what you call de facto standards. Um, Perhaps they are just like, you could argue they're just what is in OpenFOAM, what is in, settings in certain example cases, um, standards in, sort of certain algorithms that there's a kind of implied consensus that they're the ones that are going to be used because everybody's using them in OpenFOAM, right? Um, like the momentum predictor example. Do we solve that? Do we solve the momentum equation or do we not solve the momentum equation? Well, if you want to know the answer to that, then, I'm bound to say, come on our new training course. But then one of the reasons I'm bound to talk, I think a fair reason why I'm bound to say that is because we're the organization developing and maintaining OpenFOAM that's released through the foundation. So we know very well what you should be doing with Momentum Predictor. As I mentioned earlier anyway, Henry Weller was the guy who suggested it in the first place over 2 decades ago. So I'm bound to say, of course, that I think companies should send people on our training, otherwise where they're going to get it from. I think one thing in particular is
Sure.
that, and this is another kind of complaint, or when I mention this on training, everybody tends to kind of agree, which is don't assume that the fluid dynamics aspect is going to be learned at kind of undergraduate university courses and so on. And the reason is that what they teach in those courses is not really extremely relevant to CFD. The main reason is because in those courses they're teaching things that can be tested by written examination, right? So, if you're doing, I don't know, flow around a sphere, they'll have Stokes flow, and they'll go through maybe the analytical solution, and they'll get you to try and do that in the exam. But that doesn't really help you when you want to do CFD, partly because the solution is only valid for Reynolds number of 1 or below. And anyway, doing having in mathematics the agility to kind of do that solution is also not a skill that particularly useful in CFD, right? So yes, it's pen and paper solutions that they're sort of teaching, but CFD is precisely not pen and paper solutions. That's the point. If I could do it with a pen and paper solution, if I have a problem I can solve with that, I'll do it pen and paper. And those are being done. And I think that one aspect, apart from the solutions being simple, I'll give you a good example, right? Is that they tend to cover, say, systems. So you'll learn something relevant to a system. What CFD is for is to looking inside the system and analyzing the detail. So if you take, say, undergraduate teaching, you'll learn first law of thermodynamics. Now, that's just conservation of energy applied to a system. And in CFD, what we need to know is conservation of energy. So that bit of teaching, first law of thermodynamics, in the way it's presented, is kind of irrelevant. We want to learn conservation of energy, which is the equation in detail that applies within the system, not to the system in a sense. And that's sort of, so again, with the book, that's kind of what I was doing. I was trying to put information in there that was relevant to CFD, and in the new course, Principles of CFD, it's really about making the connections between those information and the design and evaluation stages of the CFD process. I mean, when I ask if I have one thought on this, if you think about, say, doing a problem, let's say you do aerodynamics around a car, what is it that you take from your undergraduate learning that you can use to help you with that problem? And I really think, at least my undergraduate, I know it's quite a while ago, but my undergraduate teaching, there's not a lot that I can take. And I don't think that's changed very much. And that's when I pose that question to people on training, they kind of agree. They seem to say, yeah, I agree with that. And certainly, Stokes's flow around a sphere is not going to help you because it's not Reynolds number 1. Yeah. So, no, I know the question was about, how do you ensure you've got enough well-trained engineers? And I don't really know an answer other than go and get them trained, but don't rely on university kind of undergraduate training, and don't even rely on necessarily, postdoctorate training, because I've mentioned before, I keep getting told by people on our training that their supervision is not, is not adequate. And I'll qualify them, right? The reason why is because most people doing PhDs that use CFD, the supervisor is an expert in the physics that is involved. That's why they get funded. That's where their reputation lies. But they do CFD as part of the PhD project, but they themselves are not experts in CFD. They don't use it day to day. They may have never ever used it at all. And they just take the approach where they say, oh, that thing OpenFOAM, it's free. Just go and get that and use it and do this, that, and the other. And they can't back it up with very much. And I think, while I've mentioned that in the academic context, you could probably say the same in industry as well. But I think it's
Mhm.
a big issue. I think, one other aspect is that we sort of noticed that there's a lot of uh, stimulation being used, let's say, for development of net zero technologies. And, and so I can imagine a big demand or big need for CFD people in that field, partly because as soon as you mention those technologies and you talk about CFD, we say fluid dynamics, but what we really mean is fluid dynamics, heat and heat transfer, thermodynamics, possibly chemistry, particles. So those things are all absolutely at the heart of net zero technology. I mean, it's about energy, right? And moving energy around. So I think there's going to be, if I think there already
Yeah.
is, an emerging demand around that, around that technology, those technologies. So I don't have all the answers, but you know,
Yeah.
get them trained, and and obviously I'm bound to like suggest us. And I can't, you know, can't lie about it.
Of course. Yeah. Well, that's another thing too. And the note of managers, my observation has been that, and you've noted this, that there's pressure from supervisors, right, to perform and to do stuff. But one misconception I think that students have too is that all learning should be free. Everything should be free. Textbooks and everything should be free. And it's like I at some point, if you really want to become an expert, you've got to invest your own resources in getting training to become an expert. And I think that's been an observation that I've seen of students reaching out to me for help, and I just can't help. And I got an email this morning. Someone's working on a master's project and they reached out to me to ask for help. And my first response is, this is between you and your supervisor. I'm not on your committee. I have no obligation. Like, you're not paying me, and that would be wrong in multiple ways if you were a research student paying me. But there's a misconception on how it's a two-lane street, is all I'm saying. That some people have a big misconception on how the training should be received, and calibrating expectations to reality there, because you're not able to.
Yeah,
Isn't
I
it?
mean,
Open foam would
and
suffer if you
people
went
don't,
around giving training for free.
people just don't
You can't do
understand that
that. That's not a
it's
business. So
it's a huge investment to create, say, a new course, right? The amount of time we spend. I mean, if I take the book, even writing the book, uh, we, it'll take a, it'll take a decade probably to see a return on the time that we spent doing that. So we have given something there that, um, that
that is
our,
free online, right?
yeah, putting
Yeah,
online,
yeah.
and it's come,
That
it's
is
our
free
money of
online,
like
right?
putting,
You
putting that,
yeah,
putting that
yeah.
out.
Mhm,
Um, I can't remember. I think the
mhm.
writing the book was something like 800 hours. So it's something of that order. And it, yeah, it kind of took its toll a little bit.
Yeah,
When you write in the middle of it, yeah, even left, you just,
yeah,
you when you sleep at night, your dreams are kind of going around topics and stuff. It was tough going. Yeah. Um. Anyway, so, but anyway, also what you say is about people contact. We get that all the time. I mean, we're inundated with people just saying, can you help me do this? Can you help me do that? Um, and
mhm,
and we have to give them
yeah,
often the same response. You've got a supervisor, and their response back is, yeah, but my supervisor isn't giving me any help. Well, see earlier conversation that we see that everywhere, right? And I'm not, coming back to it. I understand why that's the case,
yeah,
because what it really implies is that there aren't enough supervisors coming on our
mhm,
training,
yeah,
right? Yeah, that they are not doing the CFD training, and I think a little bit
yes,
of a reason for that is it's just a little bit kind of times it's ego and posturing, right? They just don't want to be seen to have to get some training on something that's labeled computational fluid dynamics when they are a member of faculty or whatever of fluid dynamics, right? So that's part of the problem. And actually, that's a whole different conversation. But posturing and ego is something that gets in the way a lot in CFD. I think in our experience in CFD.
Yeah. Two comments. Winston Churchill had a comment about writing, and he said, at first you write the book and you're in love with it, and then by the end of it, you just throw it out the door to be published because you're so sick of it. Just of like the process. And I'm working on a book, and not that it was just a humorous way of talking about how it changes. You're excited about the project, and then in the middle of it, it's just so consuming. And by the end of it, you're just like, I just want to publish and be done.
In particular with the book, I got through. So I had an idea at the outset. I'll give you this. If we've got time, I'll just explain quickly something here you might find funny. So at the outset, I kind of thought, I had ideas roughly how many pages. I thought it was going to be about 160 pages. And I was thinking that there were the 5 chapters that get us to chapter 5. And then they were going to be about 20 topics. And that worked out about right. And then I thought, I don't know why I thought this. I thought, right, I'm going to then do a topic on turbulence, but it's going to be half the length of the other topics. It turned out to be, or a chapter, it turned out to be twice the it turned out to be 2 chapters. So it was twice the length of everything else. I don't know why I got that. So 6 and 7, they were meant to be
was that 6 and 7
of that size. I don't know why I even thought that. I don't know what I was thinking. Anyway, so that dragged the process on a little bit. But by the end of 2021, we had the 7 chapters. And we kind of printed them out, and Henry had a copy, I had a copy, and we just said, let's read this ourselves all the way through, front to back, independently, and then we'll come together and say what we think. And we came together, and I think actually we said, okay, let's not bias our judgment here. Let's just write down the first impression we have, and then compare. And we both kind of had, it needs something that ties it together at the end. And that's when the chapter 8 came along. And I was, and I kind of thought, oh yeah, I know I've got to do this. But this is the point I have the kind of Churchill's experience where I just think, I just want to get this out the door. It took something like, because I was fitting it in around everything else. It took from January toward, it was April when we got it published. So kind of 3 months or whatever. And I'm not a big fan of documenting in a book example cases. I don't really think they achieve very much. I think example cases are for distribution with the code. Just basically writing things saying the viscosity is this, the flow speed is that. So what? And then having a picture of the result. I'm not sure what it achieved. But of course, then you publish the thing, and then quite quickly some review comes in saying there aren't enough examples. Well,
it's like
anyway, I at that point I just wanted to get it out the door. But funnily enough, I go back to it myself. It's almost like, half the time I just forget things. And so I go to the online version and just, because I know where everything is, and I go back just to check a few things from time to time, particularly writing the new course that we're doing. And on the new course, we're kind of referencing the book so people can essentially get more background information with each thing we discussed. So there's a lot of kind of cross-referencing. The training's not about just bombarding people with knowledge. It's about teaching processes, procedures, workflows. Call it what you like. That's what you have to. And that's what makes good quality training, is focusing on that. and not making it a knowledge bombardment exercise. It's about process and workflow. It's about which is all about building that
Yeah.
competency, confidence, and all that.
Yeah. Yeah. Thank you. Really, really insightful discussion on this. I want to pivot now to one of the themes I hear. Can you give examples of how OpenFOAM is being used in private companies throughout the world? And are these examples specific to these companies' workflows, or are you feeling like there are loads more companies that could be deploying OpenFOAM in their
Yeah,
workflow
yeah.
instead of commercial software,
I think
or in conjunction with commercial software?
so. First thing is, I think we can't underestimate how much OpenFOAM is being used um, compared to commercial software.
Mhm.
The, of course, we can't necessarily know because we don't because it's not a licensed product. We don't have we don't know how many licenses
Yeah.
there are.
Yeah.
But if you look on a
Yeah.
few
Yeah.
about a year ago, I think I looked on LinkedIn and looked at job adverts, and okay, this might have been one day, whatever, but job adverts don't come and go that quickly. I counted more job adverts for OpenFOAM with OpenFOAM experience than the kind of big two commercial CFD codes put together. So
Yeah.
by about 30% more. So I I think that
Yeah.
I think OpenFOAM
Hmm.
has got plenty of use out there.
Yeah.
I think as well that I wouldn't underestimate. I wouldn't sort of
Yeah.
just think that it's big organizations that have resources to kind of plug OpenFOAM into their own set of workflows. I think there are just people who may come on our training and just go, right, well, I use the workflows that I'm being taught on the training, and that's how I'm going to do my CFD in OpenFOAM. So I think there's just as many sort of small groups as there
Yeah.
are, you know, of people in small or one person groups that using OpenFOAM as there are the kind of big groups.
Mm-hmm.
But in larger organizations, that there are more
Yeah.
ambitious things that can be done. And um, we published something last year about the work we've done with Wärtsilä in Finland, where essentially they've said, we want to build an engine capability to Wärtsilä. People who don't know, it's a Finnish company who creates marine engines, huge marine engines, and so they wanted a capability that can just do engine simulations in OpenFOAM. So they're a kind of example customer where they contract us to do developments. They're also funding kind of general maintenance of OpenFOAM and being quite proactive about that, getting partner organizations to put money towards the maintenance effort. And I'm pretty sure that with working that way, they've got a solution, they've got something going, which they've managed to do very, very quickly by working with us. And the reason why, I mean, in a way, the reason why things can be done quickly is because I think now we've got a very robust code with, kind of robust general functionality. And what happens in the case like with Wärtsilä is we're largely enabling that functionality for particular applications. So it's just combining things in ways that we haven't combined before, that's the So I think there's astonishing things that can be done, like that within private companies. If they either I suppose working without us or working with us.
Mm-hmm. Living in Asia and Europe are using OpenFOAM. One of them was hired specifically to make the transition from a commercial tool to OpenFOAM and to templatize things and kind of streamline for the rest of the team. And then the other one's regularly using OpenFOAM. And so I don't even think that I had acknowledged and realized that it's both industrial settings and it is like, yeah, even within my small circle of that. So that was just interesting. Um, what Switching gears here again, what recent trends or advancements get you excited about CFD, right? When you think of where we're headed with CFD tools, maybe the next improvements or developments being incorporated or tested in OpenFOAM, what gets you excited about those things, and what are those topics?
Well, this answer might sound kind of boring, right? But basically, what we've established with the development of OpenFOAM in recent years is there's kind of two governing principles that we adopt, and the first one is that we're aiming to produce kind of general, reusable, and importantly, consistent functionality. So it's all about code that, like, if you're gonna do something in the code, we want one way of doing it.
Mm.
Let's say one function that does it and no more. So that, and if you, so a good example would be, let's say you've got a function that's calculating the heat flux through faces of cells or at a boundary or whatever. We want one function name that does that. And if there's only one function defined, there's only one way of doing it. So you're going to have consistency because there's only one way. Right? So, and I think that effectively then, you could also claim that's generality, but and the two go hand in hand.
Mm-hmm.
General reusable ways of doing things are going to cause consistency. So with that, what I've seen over the last, I don't know, 5 to 10 years is gradually CFD with OpenFOAM has lost its kind of it's lost a lot of unreliability to the point where now I think if something blows up, if something's not working well, you've got a much better chance of putting your finger on it. That there's a much narrower range of things that could have gone wrong. I should say then the second principle is implementing conservative numerics on using numerical methods that are conservative, meaning that we obey mass conservation. And what people don't, and you might think that's quite a detailed thing to be part of these two governing principles, but what people don't really understand is that conservation is it's not so much about accuracy. If you're not mass conservative, the problem isn't that, oh, well, the solution is going to be a little bit inaccurate because you haven't obeyed the mass conservation equation. The problem is it has an effect on boundedness, which then, precisely that it makes things go unbounded, which then makes things unreliable. And if you are doing like an internal combustion engine with moving pistons, like, the thing that I didn't quite fully describe, but what I was talking about moments ago, then you need everything on your side to make sure that simulation hangs together. And if one element somewhere is non-conservative, then that can cause the whole thing to blow up. So it's about saying everything we do is going to have conservative numeric. And since that sort of realization, since that approach, things like replacing AMI, which was a kind of coupling interface with something called NCC. The difference being that NCC is conservative and AMI isn't. So we kind of got rid of non-conservative stuff, brought in conservative stuff. Suddenly, then you can, as I say, do these more challenging things, particularly about coupling. It's particularly about multi-region simulation. So in a way, multi-region simulation is I think the thing now that we are in a much better position to do. The last sort of I think that the last piece that really enabled that was modular solvers. Now, modular solvers, the difference. So I mentioned icofoam earlier, where each fluid, each sort of fluid itself was represented by its own application, its own solver code that described whatever physics were involved with that fluid. And things like icofoam contained algorithm structure as well as equations. What we have now with modular solvers is that there's one solver which just contains a generalized algorithm. So it's the algorithm structure, and then you plug in modules that describe what happens in each stage of the algorithm. So you populate the functions in that algorithm in different ways depending on the fluid module, which is describing in effect what type of fluid or what fluid physics you're incorporating. And having done that, you've got this one solver, which is the definitive algorithm. And to make that work for multiple regions, all you do is for every function, you just loop over each region. So the extension from single to multi-region was just trivial. I mean, actually kind of trivial. Boundary conditions are required to do the coupling, but again, we've generalized much better sort of things like temperature boundary conditions for coupling. So it's enabled multi-region flow in a way that we couldn't have imagined a few years ago. But when I think of modular solvers, it gives me a kind of buzz that, like when I first saw icofoam in 1996. For me, modular solvers is the most, in itself, the most exciting thing, because conceptually we changed the sort of way we think about things and separated algorithm from physics, I suppose. And in a way, that's what OpenFOAM was always about, because, it was always about modularity. It was all about exploiting features of the C++ language, object orientation, class hierarchies, and sort of inheritance and all that. But we never had that on the application side. To have it on the application side now is fantastic. And you never know, people might, detractors might say, well, why do you need that? The thing is, you don't know, until you have it. But then I could always kind of go back to the start of this conversation and say, when I first saw icofoam in 1996, I imagined there were all these possibilities that turned out to be true. And I've got the same feeling now for modular solvers. Yeah. So you don't know what necessarily around the corner, but you've got a better chance of it being exciting if you've got the code in the right place, if you've got generality, reusability, consistency, and robust conservative numerical methods.
So to summarize, this is a higher level change of excitement. It's the organizational structure that gets you excited for the flexibility and versatility moving forward for whatever specifics come. You're solving one problem rather than 50 tiny problems. It's always the generalization, and that is something you pointed out. Yeah.
That's right. And I think that, I think that those are things also that excite the, Henry Weller, Will Bainbridge internally, as maintainers and developers, because the question is what's going to limit progress. In the end, progress just gets limited because the code that you have becomes too difficult to work with. So they're not so much thinking about what the new features are. They're thinking about having something in place that can enable the development of new features with minimal pain. Right?
Yeah.
So they see it from that perspective, because they're the ones who are kind of going to have to get, they're the ones who kind of have to experience the pain. Yeah. But for me, I even think about it, from a training perspective, that talking about, explaining modular solve is just easier to do. And even on the programming training course we have, we talk about, we do a lot about developing a solver module that I wouldn't have attempted to do with the old application solver. I didn't do because it was too complex before. Whereas now, in a more modular structure, it's just easier. It's just easier to do and understand. So I think that users, maybe, people doing things like PhDs or people doing research in companies, like they should really embrace solver modules, these modular solvers, because it should make their job easier. All it requires is that they just learn a bit more about programming. So they just need to do a bit more work on doing C, understanding C++. They can come on our programming course, but however they want to do it, they just need to do a bit more programming. But the benefit for particularly things like maintaining their capability in-house, if they've got some developments, maintenance is so much easier in a new framework. So I think it offers new. I think it's going to enable more rapid progress.
Exciting. That's really exciting. You've shared tons of advice, and by asking this question, I don't mean to discount any of that, but kind of the culmination of what do you know about CFD now that you wished you would have known when you were starting your career?
Well, my immediate thought when you say that is kind of nothing. But the reason is because obviously the question is hypothetical, right? But what I've witnessed and been involved in around OpenFOAM is a kind of, was a sort of process of discovery. So the things that we know, or I know, we kind of, I'm not saying we invented, but well, in some cases, yes, but we kind of, that the exciting thing was learning about, was discovering them. And I don't, we don't want, obviously I don't want everybody to have to go through that process, right? That's the point of writing the book. It's the point of doing the training. It's the point of even distributing a code for free. It's to make things that essentially, that if we take the code, for example, the idea is that the ideas and the knowledge is encapsulated within that code. And if the source code is open, then people can, learn from that and infer things from that themselves. So we're not really in a position to, I'm not this kind of person who wishes anything is different, to be honest. But I guess what's maybe what I wished is it's not about the CFD itself. It's almost as if that my excitement about something like IcoFoam, I kind of wished I knew that wouldn't resonate with other people. So essentially that a lot, things I wished I knew were more about, I don't know, business things around what we do, not actually in relation to specifically what we do around CFD. So how companies would respond to OpenFOAM, I kind of wished I knew it. Thinking about things, the fact that people don't necessarily share any excitement that I might have, or Henry might have, or Will has about the software, but instead be kind of suspicious about it being open source. Rather than embracing it, actually be positively kind of suspicious and about it. Those kinds of things. It's just attitude. And I wish I knew that people, maybe in France, that people were generally very conservative and risk averse, if you see what I mean. Which affects the way they the affects their interaction with us, the adoption of OpenFOAM, the funding of OpenFOAM and that kind of thing.
Yeah.
So it's nothing to do with what I wish I knew. Maybe it's nothing to do with CFD. It's to do with the environment that we ended up in by producing this thing which is open source and free and whatever. Although, and those are things that I think we couldn't have known so much because when we released OpenFOAM in 2004, it was really early days, I think, of open source software, or, if there was a kind of brief open source movement, it was around that time. So there was sort of, let's say, promises of what open source would bring, but we hadn't, but the reality's been quite different.
Yeah.
And even if we sort of know, I don't think we could have anticipated how things would be slightly different. That the big thing that we maybe couldn't anticipate is that open source works very well in terms of getting funding, etc., in environments where the beneficiaries are in the software industry. So, and the reason that works is because they understand what it takes to produce the software. So if you're talking about, say, the Linux kernel, of course, like big companies will sponsor that because they are, it's tech companies that are doing that. Linux is tech as in software. They get it, or whatever. Whereas the beneficiaries of OpenFOAM are like engineers, and they just don't understand 99% at least what it takes to produce a piece of software like OpenFOAM. So I think that translates into a kind of ambivalence about funding open source, which we probably couldn't have anticipated.
Yeah.
Of course, the other thing is that, with certain bits of software or certain projects, if you take, say, Wikipedia, because there's so many users, even if you get a small fraction of them funding the project, it's quite a lot of money. And I think Wikipedia talks about around about 0.1% of people funding. Well, if we said we had, say, 20,000 users of OpenFOAM, then that's 20 people, right? So it's a numbers game, right?
Yeah.
But I'm not excusing industry or academia, for that matter, for the lack of funding for us entirely. And particularly, a particular reason for that is because of the cost they're saving compared to commercial license fees. I would have thought that it would be a compelling economic argument to say, if you're saving, this license fee, then still nevertheless, fund maybe 10% of that towards maintenance of an open source product. But the reality of that isn't that it just didn't happen. And I'll give you one anecdotal piece on that. Once I was talking to a guy who'd had $800,000 of license fees, and in his company, and they started using OpenFOAM, and he told me about 2 years later the great news, which was they've managed to shed 400,000, so they reduced their license fee bill by 50%. So I said to him, well, can you go to the company accountant and suggest that even they give us 10% of that towards maintaining OpenFOAM? And he said, no, they're never going to buy that. What they will do is if they'll give you sort of another $40,000, if you can get rid of our other $400,000 of license fees. And that doesn't make economic sense. I mean, it's not a good deal. So I wish to sort of knew that, maybe.
Yeah.
Which is more a question of, I don't know, sociology, not physics or science.
Yeah.
Maybe economic. But if I knew more about economics, I'd be in a better position to anticipate this kind of stuff.
Yeah. Well, Thank you so much for the discussion today, Chris. It's been really, really insightful. Really enjoyed our discussion, and thank you again for coming on the show.
Thanks, Kate. Great to meet you, and thanks for inviting me to your podcast, which seems to be incredibly successful. I don't know, you're always getting 20 of these things or so.
Yeah, I think by the time this releases, we'll be upwards of 22 or so. Thank you. Yep. Thank you for listening. Really, thank you. Did something about this episode stand out to you? If so, please go ahead and share it with others on LinkedIn or other social media so they can find this as well. See you next time.